The NIM Programming Language. NIM Tutorial, Part Roman 3. Author, Andreas Rumpf. Version, 2.2.2. Introduction. This document is a tutorial for the advanced constructs of the NIM programming language. Pragmas. Pragmas are NIM's method to give the compiler additional information and commands without introducing a massive number of new keywords. Pragmas are enclosed in the special curly dot and dot curly brackets. This tutorial does not cover pragmas. See the manual or user guide for a description of the available pragmas. Object-oriented programming. While NIM's support for object-oriented programming, OOP, is minimalistic, powerful OOP techniques can be used. OOP is seen as one way to design a program, not the only way. Often a procedural approach leads to simpler and more efficient code. In particular, preferring composition over inheritance is often the better design. Inheritance. Inheritance in NIM is entirely optional. To enable inheritance with runtime type information, the object needs to inherit from root obj. This can be done directly or indirectly by inheriting from an object that inherits from root obj. Usually types with inheritance are also marked as ref types, even though this isn't strictly enforced. To check at runtime if an object is of a certain type, the of operator can be used. Type person equals ref object of root obj. Name asterisk. String hash the asterisk means that name is accessible from other modules. Age. Int hash no asterisk means that the field is hidden from other modules. Student equals ref object of person hash student inherits from person. ID. Int hash with an ID field. var student, student. Person, person. Assert, student of student, hash is true. Hash object construction. Student equals student, name. Anton, age, 5, ID, 2. Echo student. Inheritance is done with the object of syntax. Multiple inheritance is currently not supported. If an object type has no suitable ancestor, root obj can be used as its ancestor, but this is only a convention. Objects that have no ancestor are implicitly final. You can use the inheritable pragma to introduce new object roots apart from system.rootObj. This is used in the GTK wrapper, for instance. Ref objects should be used whenever inheritance is used. It isn't strictly necessary, but with non-ref objects, assignments such as let person equals student ID 123 will truncate subclass fields. Note: composition as a relation is often preferable to inheritance is a relation for simple code reuse. Since objects are value types in NIM, composition is as efficient as inheritance. Mutually recursive types. Objects, tuples and references can model quite complex data structures, which depend on each other. They are mutually recursive. In NIM, these types can only be declared within a single type section. Anything else would require arbitrary symbol lookahead, which slows down compilation. Example. Type node equals ref object hash a reference to an object with the following field. Right, node hash left and right subtrees. Sim. Ref sim hash leaves contain a reference to a sim. Sim equals object hash a symbol. Name. String hash the symbol's name. Line. Int hash the line the symbol was declared in. Code. Node hash the symbol's abstract syntax tree. Type conversions. NIM distinguishes between typecasts and type conversions. Casts are done with the cast operator and force the compiler to interpret a bit pattern to be of another type. Type conversions are a much more polite way to convert a type into another. They preserve the abstract value, not necessarily the bit pattern. If a type conversion is not possible, the compiler complains or an exception is raised. The syntax for type conversions is destination type expression to convert, like an ordinary call. Proc get ID x person int equals student x dot ID. The invalid object conversion defect exception is raised if x is not a student. Object variants. Often an object hierarchy is overkill in certain situations where simple variant types are needed. An example. This is an example how an abstract syntax tree could be modeled in NIM. Type node kind equals enum hash the different node types. Nkint hash a leaf with an integer value. Nkfloat hash a leaf with a float value. Nkstring hash a leaf with a string value. Nkadd hash an addition. Nksub hash a subtraction. Nkif hash an if statement. Node equals ref object. Case kind. Node kind hash the kind field is the discriminator of nkint int val int of nk float, float val, float, of nk string, str val, string, of nk add, nk sub, left top, right top, node, of nk if, condition, then part, else part, node, var n equals node, kind, nk float, float val, 1.0. Hash the following statement raises an field defect exception because n.kind's value does not fit. n.strval equals. As can be seen from the example, an advantage to an object hierarchy is that no conversion between different object types is needed. Yet, access to invalid object fields raises an exception. Method call syntax. There is a syntactic sugar for calling routines. The syntax obj.method name, args, can be used instead of method name, obj, args. If there are no remaining arguments, the parentheses can be omitted, obj.len, instead of len, obj. This method call syntax is not restricted to objects, it can be used for any type. Import std/strutils. Echo abc.len hash is the same as echo len abc. Echo abc. To upper ASCII. Echo abc.card. stdout.writeLine, hello, hash the same as writeLine, stdout, hello. Another way to look at the method call syntax is that it provides the missing postfix notation. So, pure object-oriented code is easy to write. Import std/strutils, sequitils. stdout.writeLine, give a list of numbers, separated by spaces. stdout.write, stdin.readline.split whitespace.map, parseInt.max, $. stdout.writeLine is the maximum. Properties. As the above example shows, NIMP has no need for get properties. Ordinary get procedures that are called with the method call syntax achieve the same. But setting a value is different. For this a special setter syntax is needed. Type socket asterisk equals ref object of root obj. H. Int hash cannot be accessed from the outside of the module due to missing star. Proc host equals asterisk s. Var socket value int dot inline equals hash hash setter of host address. Sh equals value. Proc host asterisk s socket int dot inline equals hash hash getter of host address. Sh var s socket new s dot host equals 34 hash same as host equals s 34. The example also shows inline procedures. The array access operator can be overloaded to provide array properties. Type vector asterisk equals object x, y, z, float. Proc brackets equals asterisk v, var vector, I, int, value, float, equals hash setter. Case I of 0, vx equals value. Of 1, vy equals value. Of 2, vz equals value. Else, assert false. Proc brackets asterisk v, vector, I, int, float equals hash getter. Case I of 0, result equals vx. Of 1, result equals vy. Of 2, result equals vz. Else, assert false. The example is silly, since a vector is better modeled by a tuple, which already provides v brackets access. Dynamic dispatch. Procedures always use static dispatch. For dynamic dispatch, replace the proc keyword by method. Type expression equals ref object of root obj hash hash abstract base class for an expression. Literal equals ref object of expression. X, int. Plus exp equals ref object of expression. A, B, expression. Hash watch out, eval relies on dynamic binding. Method eval e, expression, int dot base, equals. Hash overrides this base method. Quit to override. Method eval e, literal, int equals ex. Method eval e, plus exp, int equals eval ea, plus eval eb. Proc new lit x, int, literal equals literal x, x. Proc new plus a, b, expression, plus exp equals plus exp a, b, b. Echo eval new plus new lit 1, new lit 2, new lit 4. Note that in the example the constructors new lit and new plus are procs because it makes more sense for them to use static binding, but eval is a method because it requires dynamic binding. Note, starting from nim 0.20, to use multi-methods one must explicitly pass -- multi-methods on when compiling. In a multi-method all parameters that have an object type are used for the dispatching. Type thing equals ref object of root obj. Unit equals ref object of thing. X. Int. Method collide a, b, thing dot inline equals quit to override. Method collide a, thing, b, unit dot inline equals echo 1. Method collide a, unit, b, thing dot inline equals echo 2. Var a, b, unit, new a, new b, collide a, b, hash output 2. As the example demonstrates, invocation of a multi-method cannot be ambiguous. Collide 2 is preferred over collide 1 because the resolution works from left to right. Thus unit, thing is preferred over thing, unit. Performance note: NIM does not produce a virtual method table, but generates dispatch trees. This avoids the expensive indirect branch for method calls and enables inlining. However, other optimizations like compile time evaluation or dead code elimination do not work with methods. Exceptions. In NIM, exceptions are objects. By convention, exception types are suffixed with error. The system module defines an exception hierarchy that you might want to stick to. Exceptions derive from system.exception, which provides the common interface. Exceptions have to be allocated on the heap because their lifetime is unknown. The compiler will prevent you from raising an exception created on the stack. All raised exceptions should at least specify the reason for being raised in the MSG field. A convention is that exceptions should be raised in exceptional cases. They should not be used as an alternative method of control flow. Raised statement. Raising an exception is done with the raised statement. Var e, ref OS error. New e. E.msg equals, the request to the OS failed. Raise e. If the raised keyword is not followed by an expression, the last exception is re-raised. For the purpose of avoiding repeating this common code pattern, the template new exception in the system module can be used. Raise new exception, OS error, the request to the OS failed. Try statement. The try statement handles exceptions. From std/trueTils import parseInt. Hash reads the first 2 lines of a text file that should contain numbers and tries to add them. Var f, file. If open, f, numbers.txt. Try. Letter equals readline f. Let b equals readline f. Echo, sum. ParseInt a plus parseInt b. Except overflow defect. Echo, overflow. Except value error. Echo, could not convert string to integer. Except IO error. Echo, IO error. Except catchable error. Echo, unknown exception. Hash erase the unknown exception. Raise. Finally. Close f. The statements after the try are executed unless an exception is raised. Then the appropriate except part is executed. The empty except part is executed if there is an exception that is not explicitly listed. It is similar to an else part in if statements. If there is a finally part, it is always executed after the exception handlers. The exception is consumed in an except part. If an exception is not handled, it is propagated through the call stack. This means that often the rest of the procedure that is not within a finally clause is not executed if an exception occurs. If you need to access the actual exception object or message inside an except branch, you can use the getCurrentException and getCurrentException MSG procs from the system module. Example. Try, do something here. Except catchable error. Let e equals getCurrentException. MSG equals getCurrentException MSG. Echo.exception, repr e, with message, MSG. Annotating procs with raised exceptions. Through the use of the optional .raises. Pragma, you can specify that a proc is meant to raise a specific set of exceptions, or none at all. If the .raises Pragma is used, the compiler will verify that this is true. For instance, if you specify that a proc raises IO error, and at some point it, or one of the procs it calls, starts raising a new exception, the compiler will prevent that proc from compiling. Usage example. Proc complex proc.raises. IO error, arithmetic defect brackets dot, equals. Proc simple proc dot, raises, brackets dot, equals. Once you have code like this in place, if the list of raised exception changes, the compiler will stop with an error specifying the line of the proc, which stopped validating the pragma, and the raised exception not being caught, along with the file and line where the uncaught exception is being raised, which may help you locate the offending code, which has changed. If you want to add the .raises Pragma to existing code. The compiler can also help you. You can add the dot effects Pragma statement to your proc, and the compiler will output all inferred effects up to that point. Exception tracking is part of NIM's effect system. Another more roundabout way to find out the list of exceptions raised by a proc is to use the nimdoc command, which generates documentation for a whole module, and decorates all procs with the list of raised exceptions. You can read more about NIM's effect system, and related pragmas in the manual. Generics. Generics are NIM's means to parameterize procs, iterators or types with type parameters. Generic parameters are written within square brackets, for example foo-t. They are most useful for efficient type-safe containers. Type binary tree asterisk t equals ref object hash binary tree is a generic type with generic param t. Right binary tree t hash left and right subtrees may be nil. Data t hash the data stored in a node. Proc new node asterisk t data t binary tree t equals hash constructor for a node. New result data equals data. Proc add asterisk t root var binary tree t n binary tree t equals hash insert a node into the tree. If root equals nil, root equals n. Else var it equals root. While it not equals nil. Hash compare the data items. Uses the generic CMP proc that works for any type that has a equals and less than operator. Var c equals CMP it dot data n dot data. If c 0, if it dot l equals nil, it dot l equals n. Return it equals it dot l. Else if it dot ri equals nil, it dot ri equals n. Return it equals it dot ri. Proc add asterisk t root var binary tree t data t equals hash convenience proc add root new node data iterator preorder asterisk t root binary tree t equals hash preorder traversal of a binary tree. This uses an explicit stack, which is more efficient than a recursive iterator factory. Var stack sec binary tree t equals at root, while stack.len 0. Var n equals stack.pop, while n not equals nil. Yield n.data. Add stack n.write hash push right subtree onto the stack. N equals n.le hash and follow the left pointer. Var root binary tree string hash instantiate a binary tree with string. Add root new node hello hash instantiates new node and add root world hash instantiates the second add proc. For str in preorder root st.writeline str. The example shows a generic binary tree. Depending on context, the brackets are used either to introduce type parameters or to instantiate a generic proc, iterator or type. As the example shows, generics work with overloading. The best match of add is used. The built-in add procedure for sequences is not hidden and is used in the preorder iterator. There is a special :t brackets syntax when using generics with the method call syntax. Proc foo t brackets I:t equals discard. Var I int hash I dot foo int brackets hash error expression foo I has no type or is ambiguous. I dot foo int brackets hash success. Templates. Templates are a simple substitution mechanism that operates on NIM's abstract syntax trees. Templates are processed in the semantic pass of the compiler. They integrate well with the rest of the language and share none of C's preprocessor macros flaws. To invoke a template, call it like a procedure. Example. Template not equals AB, untyped, untyped equals. Hash this definition exists in the system module. Not A equals B. Assert 5 not equals 6, hash the compiler rewrites that to assert not 5 equals 6. The not equals, greater than equals, in, note in, is not operators are in fact templates. This has the benefit that, if you overload the equals operator, the not equals operator is available automatically and does the right thing. Except for i.e. floating point numbers, NARN breaks basic Boolean logic. A greater than B is transformed into B less than A. A in B is transformed into contains B, A. Not in, and is not of the obvious meanings. Templates are especially useful for lazy evaluation purposes. Consider a simple proc for logging. Const debug equals true. Proc log msg string dot inline dot equals. If debug st out dot write line msg var x equals 4. log x has the value ampersand $x. This code has a shortcoming. If debug is set to false someday, the quite expensive dollar and ampersand operations are still performed. The argument evaluation for procedures is eager. Turning the log proc into a template solves this problem. Const debug equals true. Template log msg string equals. If debug st.writeLine msg var x equals 4. Log x has the value ampersand $x. The parameters types can be ordinary types, or the meta types untyped, typed, or type suggests that only a type symbol may be given as an argument, and untyped means symbol lookups, and type resolution is not performed before the expression is passed to the template. If the template has no explicit return type, void is used for consistency with procs and methods. To pass a block of statements to a template, use untyped for the last parameter. Template with file f, untyped, file name, string, mode, file mode, body, untyped, equals. Let fn equals file name. Var f, file. If open, f, fn, mode. Try, body. Finally, close, f. Else, quit, cannot open. And fn. With file, txt, ttemple3.txt, fm write. txt.writeLine, line 1. txt.writeLine, line 2. In the example, the two writeLine statements are bound to the body parameter. The with file template contains boilerplate code and helps to avoid a common bug, to forget to close the file. Note how the let fn equals file name statement ensures that file name is evaluated only once. Example, lifting procs. Import std/math. Template lift scalar proc, fname, equals. # lifter proc taking one scalar parameter and returning a scalar value, for example, proc ssss, t, x, t, float, to provide templated procs that can handle a single parameter of sec, t, or nested sec brackets, or the same type. Nim lift scalar proc, abs, #now abs at 1 2, at 2 3, equals, at 1 2, at 2 3. Proc fname, t, x, open array, t, auto equals. var temp, t. Type out type equals type of fname temp. Result equals new sec out type x.len. For I in 0 dot less than x.len. Result I equals fname x I. Lift scalar proc sqrt #make sqrt work for sequences. Echo sqrt at 4.0, 16.0, 25.0, 36.0 outputs at 2.0, 4.0, 5.0, 6.0. Compilation to JavaScript. Nim code can be compiled to JavaScript. However, in order to write JavaScript-compatible code, you should remember the following. Adder and PTR have slightly different semantic meaning in JavaScript. It is recommended to avoid those if you're not sure how they are translated to JavaScript. Cast (x) in JavaScript is translated to x, except for casting between signed and unsigned ints, in which case it behaves as static cast in C language. C-string in JavaScript means JavaScript string. It is a good practice to use C-string only when it is semantically appropriate. For example, don't use C-string as a binary data buffer. Next, part 4. The next part is entirely about metaprogramming via macros. Part Roman 4.